Ever wondered how ancient civilizations like Babylonians, Egyptians, and Greeks laid the foundation for modern mathematics? Let's embark on a journey back in time, to the era of the Babylonians, Egyptians, and Greeks. These ancient civilizations, known for their grand architectures and sophisticated societies, were also mathematical pioneers. Their early concepts and techniques laid the groundwork for what we now know as linear algebra. The Babylonians, as early as the 2nd millennium BC, were known for their expertise in handling linear equations. They developed methods to solve what we now recognize as systems of linear equations, an integral part of linear algebra. The Egyptians, on the other hand, were masters of geometry. Their mathematical prowess was evident in the precision of their pyramids, which required a deep understanding of geometric principles. These principles would later be foundational in the development of vector spaces, a core concept in linear algebra. The Greeks, with their philosophical approach to knowledge, made significant strides in abstract mathematical thought. Renowned Greek mathematician Euclid's work, Elements, is often considered the first study in the geometry of vectors, a fundamental aspect of linear algebra. These ancient mathematical pioneers set the stage for the evolution of a new discipline, linear algebra. As we delve deeper into this fascinating subject, we'll see how these early seeds of knowledge grew into a rich, diverse field that continues to shape our understanding of the world. Linear algebra owes its progress to the genius of mathematicians like Euclid, Descartes, and Gauss. Our journey through the annals of linear algebra begins with the ancient Greek mathematician Euclid. Known as the father of geometry, Euclid's work laid the foundation for the concept of vectors. His seminal work, Elements, introduced the idea of geometric entities having both magnitude and direction, a core principle in vector theory. Moving forward several centuries, we encounter René Descartes, a French philosopher and mathematician. He revolutionized mathematics by marrying algebra and geometry, resulting in the Cartesian coordinate system. This innovation allowed mathematicians to describe geometric shapes using equations, a fundamental aspect of linear algebra. Next, we meet Carl Friedrich Gauss, a German mathematician who made significant contributions to many fields, including number theory, statistics, and of course linear algebra. Gauss is particularly known for developing the method of Gaussian elimination. This technique, used for solving systems of linear equations, is a cornerstone of linear algebra. Gauss's method simplified the process of manipulating matrices, making it easier to solve complex problems. These luminaries, along with others, helped shape the field of linear algebra as we know it today. Their work, though centuries old, remains instrumental in contemporary mathematical applications. Euclid's geometric principles are used in physics and engineering, while Descartes' coordinate system is indispensable in computer graphics and robotics. And Gauss's elimination method, it's used everywhere, from calculating GPS coordinates to optimizing algorithms in machine learning. These mathematicians were not just trailblazers of their time, but visionaries whose work continues to resonate in our modern world. They saw the beauty and potential in numbers, equations, and geometric shapes, and harnessed these to solve problems and answer fundamental questions about the universe. Each of them, in their own unique way, extended the frontiers of mathematical knowledge, leaving a legacy that continues to inspire and influence. Their groundbreaking work paved the way for the modern understanding of linear algebra. The 19th century marked a significant turning point in linear algebra with the introduction of matrices. This period witnessed a seismic shift as the concept of matrices began to take shape. Mathematicians of the era were not merely spectators to this transformation, but the driving force behind it. Figures like James Joseph Sylvester, Arthur Cayley, and William Rowan Hamilton were at the forefront of this matrix revolution. Sylvester, an English mathematician, was a pioneer in matrix theory. He is credited for coining the term matrix to describe a rectangular array of numbers. His work laid the groundwork for the study of determinants and matrix algebra. Arthur Cayley, another prominent English mathematician, expanded on Sylvester's work. He introduced the idea of a matrix's determinant and the concept of matrix multiplication. His work established the rules for matrix algebra, forming a new branch of mathematics that we now know as linear algebra. Meanwhile, across the Irish Sea, Hamilton was making his own significant contributions. He developed the quaternions, a number system that extends the complex numbers. Hamilton's quaternions laid the groundwork for the development of a matrix representation for complex numbers and played a vital role in the evolution of quantum mechanics. These advancements by Sylvester, Cayley, and Hamilton set the stage for matrix algebra. They revolutionized the field of linear algebra, introducing new methods and tools to solve complex mathematical problems. This period marked the dawn of a new era in linear algebra, expanding its applications in diverse scientific disciplines. The early 20th century saw the advent of abstract vector spaces, revolutionizing linear algebra. The stage was set for a new chapter in the annals of this mathematical discipline, and the protagonists were none other than the brilliant minds of mathematicians like David Hilbert and Stefan Banach. Hilbert, a German mathematician, was instrumental in introducing the concept of infinite dimensional spaces, known today as Hilbert spaces. These spaces expanded the realm of linear algebra, allowing us to solve mathematical problems that seemed insurmountable before. Hilbert's work was a game changer, enabling the mathematical community to approach complex problems with renewed vigor and a fresh perspective. Meanwhile, Banach, a Polish mathematician, was busy making his own indelible mark on linear algebra. He developed the theory of normed vector spaces, which we now know as Banach spaces. These spaces, complete in their own right, provided a solid foundation for the study of functional analysis. Their combined efforts radically transformed linear algebra, shifting its focus from concrete examples to abstract structures. This shift was not just about changing perspectives, it was about breaking barriers, about transcending the lines of conventional wisdom, and about paving the way for a new era of innovation and discovery. This abstract framework provided the tools to tackle complex problems and laid the groundwork for modern functional analysis. And so, the tapestry of linear algebra continued to evolve, each thread woven with the ingenuity and brilliance of mathematicians like Hilbert and Banach. Linear algebra is not just a mathematical concept, but a powerful tool that shapes our world. As we venture into the modern world, we see the footprints of linear algebra in every corner of our technological landscape. In the realm of physics, linear algebra is the language that articulates the laws of the universe. From the simple mechanics of a falling apple to the intricate dance of celestial bodies, linear algebra provides the mathematical framework to make sense of it all. Turning our gaze to the field of engineering, linear algebra plays an indispensable role in designing and optimizing complex systems. Whether it's a towering skyscraper, a high-speed train, or a microchip, engineers rely on the principles of linear algebra to ensure these structures function as intended, with precision and efficiency. In the digital domain, computer science is another field deeply intertwined with linear algebra. From the graphics that bring virtual worlds to life on your computer screen to the algorithms that sort your online searches, linear algebra is the invisible hand guiding these processes. And then we arrive at the frontier of data analysis. In an age where data is the new oil, linear algebra is the machinery that extracts valuable insights from this raw information. It powers statistical models and machine learning algorithms, helping us predict weather patterns, analyze market trends, and even recognize faces in a crowd. But perhaps the most fascinating application of linear algebra lies in the realm of quantum mechanics. In this strange and counterintuitive world, particles exist in multiple states at once, and linear algebra provides the mathematical backbone to describe these phenomena. As we traverse from the macrocosm of the universe to the microcosm of quantum particles, the principles of linear algebra remain a constant companion, helping us decipher the complex language of the cosmos. From quantum mechanics to machine learning, linear algebra continues to influence our technological landscape. As we continue our journey into the future, one thing is certain: the story of linear algebra is far from over. It will continue to unravel, shaping and being shaped by our evolving understanding of the world. What does the future hold for linear algebra? As we step into the realm of tomorrow, it becomes clear that the applications of linear algebra are expanding at an exponential pace. Notably, one field where this mathematical discipline is making waves is artificial intelligence. Artificial intelligence, or AI, is transforming the world as we know it. From autonomous vehicles to voice-activated assistants, AI is everywhere. And at its core, powering these advanced systems is linear algebra. The algorithms that allow AI to learn and evolve, to recognize patterns and make predictions, are fundamentally built on matrices, vectors, and linear transformations. Deep learning models, for example, rely heavily on linear algebra. These models, which are a subset of machine learning, use artificial neural networks to mimic the human brain's decision-making process. Each neuron in these networks is connected by weights, which can be represented as matrices. Linear algebra is used to calculate these weights, enabling the model to learn and improve. Moreover, the rise of quantum computing is set to push the boundaries of linear algebra even further. Quantum bits or qubits can exist in multiple states at once, creating a vast array of possibilities for computation. Representing and manipulating these quantum states requires the sophisticated techniques of linear algebra. As we continue to push the boundaries of technology, the role of linear algebra in shaping our future becomes increasingly evident.